A hyperbola is a collection of points in the plane, the difference of whose distance from two fixed points is constant. So a definition very similar to that of an ellipse, the only difference being instead of the distances from the focuses to the point being added together, they are being subtracted. So there isn't really going to be much new to talk about, really. It really functions exactly the same as an ellipse. The formula is got in the same manner that one would get the formula for an ellipse as well. And all of the notation is the same. The C's are for where the focus is, the A is for where the vertex is, which are here and here. And like an ellipse, there are two different formulas depending on if, in this case, the transverse axis is on the x-axis, which in this drawn example it is on the x-axis, or if it were on the y-axis, in which case I would use this formula over here. And an ellipse, there was a major axis and a minor axis, and there were different formulas depending on which the major axis was. So not so much new material. I guess the only thing here that books generally like to go over, and I suppose just to reinforce things already learned in the past in algebra recently, are just the asymptotes. And I think it's pretty clear to most people that know what asymptotes are that they're going to be diagonal from each other. So I may as well just talk about how to get those formulas, because there really isn't much sense in going over the same thing again when it's really exactly the same as an ellipse. So I'll go ahead and do that. So what I'm going to need to do is just take one of my formulas, and the equations that I'm going to get for these asymptotes are going to depend on whether I have an x transverse axis or a y transverse axis. They're very similar, obviously. Most people could probably deduce that they would be slightly different, and they are. So I'm just going to do the example for this one right here, the x. So what I'm going to need to do to find these asymptotes is obviously do a limit problem. So what I'm going to do is just take the formula, and I'm going to rearrange it, and I'm going to reduce it down to where I get a bunch of x's in the denominator, have the limit as I go from x to positive infinity and x to minus infinity, and then from there see what happens. So I'm just going to use this one. So I'm just going to rearrange to get the y on one side and subtract the other garbage. I'm going to multiply by b squared. There's just no sense in wasting all that space. And my ultimate goal is just to get all the x's in as many denominators as possible, so I can get rid of them. Otherwise, if I take the limit going to infinity, it won't mean anything. So I'm going to extract x squared and a squared from this, and this will turn into 1, and then this will be the opposite. It will be a squared over x squared. And I know a lot of people forget they can do that, but if I multiply this out, x squared over a squared, I'm going to get this originally. This is going to be x squared a squared, and this is going to be x squared over x squared, which is going to cancel out and be 1, and this is going to be a squared over a squared, which will cancel out and be 1. A lot of people, at least when I help them in math, forget they can do that, especially if they don't do a lot of math. So that's something that people tend to forget all the time. Don't know why. From here, take the square root of both sides. Let's write down here. And it's going to be positive or minus bxa square root 1 minus a squared x squared. And now it becomes a limit problem. I'm just going to take the limit as it goes to x goes to positive infinity and negative infinity. I'll do positive infinity first. So here, as x goes to infinity, this denominator is going to become larger and larger and larger and larger, and eventually this is going to become infinitesimally small. And it's going to become closer and closer and closer to the square root of 1. So this is going to go to 0. It's going to approach 0 as x goes to infinity, and this stays fixed. It's going to become very, very, very small. It'll become closer and closer to square root of 1. So that means, as x goes to infinity, this is going to approach positive or minus, plus or minus b over a, and then I just write it like this. I mean, I could write b over xa, but I mean, it's the same thing. And these are my asymptotes, and I guess I'm not technically finished, but I should find out what happens when x goes to not minus infinity. And in this case, since it's x squared, a negative number times itself is going to be a positive number, so it's going to be the exact same thing. So I'm just not going to bother to write this out again. I'm also going to get the same thing as well. So these are my lines, b over a plus or minus b over ax. So this one will be positive b over ax, and this one going down this way is minus b over ax. And again, this is one for an x transverse axis. So asymptote. And this one would be slightly different. It would end up being plus or minus a over b. I'm not going to spend time doing it. If someone wants to do it, they can just use this formula instead. The a and the b are going to be reversed. That's going to be the only difference. And besides that, there really isn't much different between ellipses and hyperbolas. I know they do seem to look a lot different and they look a lot more confusing, but it's exactly the same. It's just two fixed points, and in this case, instead of adding the distances, we're subtracting them from each other. Otherwise, everything else is the same.